As 306, the very last topic we'll be considering in the content in the course of the course. So we are going into what we call further results in the theory of rings. So this is chapter 4, and we start with definitions. Like you saw in our previous classes and videos, there was a definition for homomorphism when we are looking at groups, right? Now, when we're looking at rings in particular, we have what we call a ring homomorphism, just like we had for a group homomorphism. The definitions are similar. It's just that for a ring, we have a mapping from theta, as usual, from a ring R into a ring S. Now, for definition of a ring, I'm sure you recall your definitions in 203. You could look into the video for further definition. My videos online to get the definitions if you've forgotten. Okay, so the definition of a ring is what you have a ring homomorphism. It's similar to that of a homomorphism, but then you have this criteria. You have the addition in between, and then multiplication form of it, additive, the multiplicative, and the identity form of the homomorphism. Okay, so you need to know these definitions by heart. Just like we also had for that of a homomorphism, we have the surjective ring homomorphism. Okay, we have the ring homomorphism itself when it is an isomorphism. Okay, so an isomorphic ring homomorphism. So we have that definition. So you need to know them, just like you know those for the groups. Okay, in line with that, also we also have the orthomorphism. If you remember, it had to be what? Homomorphic, injective, surjective, right? And then you have an automorphism. We also have that of a ring endomorphism, very similar. Okay, so but it's a ring map upon itself, right? It's similar, but now you're mapping with rings. Okay, we also have definition of a corner for the ring, similar definitions but notations different. Okay, and that of the image of a ring. So you need to know that too. The next definition which we're introducing is what we call an ideal. What is an ideal? So if you have a subset A of a ring, right, it is called a left ideal if it satisfies these two conditions. So if you pick A and B in the subset A, you can subtract or add the two elements, and whatever result you get will be in A. The second condition it must satisfy is that if you multiply on the left hand side the element R from the ring itself with the element taken from the set A, which is a subset of R, the result you will get will lie in A. Once these two conditions are satisfied with multiplication from the left, we say we have a left ideal. In a similar way, if you multiply on the right hand side, so it's satisfied for the right ideal, right? It will satisfy the first condition similar to the left, but then instead of multiplication from the left, you multiply from on the right hand side. So that's when you have a right ideal. Now, if it is both a left and a right ideal, we say we have an ideal. Okay, a ring ideal. Okay, so it's a proper ideal and an ideal when it's both a left and right ideal. So an ideal, left ideal satisfies these two conditions. A right ideal satisfies these two conditions. If these two, left and right, are satisfied, we then have an ideal. Okay. Next definition you need to know has to do with the quotient, which you can see on the screen. So the quotient is called the quotient ring or the residue class. Basically, if you have an ideal K and a ring R, the quotient R modulo K defined as be the coset of K in R, then it satisfies all of this. Now, if you have the collection of such quotient, the ring, this is called the quotient ring or the residue class ring of R and K. So this is the way elements in this particular quotient ring behave. They behave this way. If you pick two elements from the ring, you add them, you will get this result. If you're taking the negative part of it, you will get this. If you're multiplying them, you will get this. That's what it's saying. But then they're called what? Quotient rings or the residue class ring of R by K. Another definition you need to know is what we call a principal ideal. Now you know what an ideal is. You said it is the ideal is one which is a left and right ideal, and the left ideal satisfy what we had seen earlier. The right ideal satisfy what we had seen earlier. But then now we have a principal ideal. Now a principal ideal in a ring R is an ideal I that can be generated by a single element A in R. So if A in R can generate all the elements in I, then we have a principal ideal. Basically, this means that every element in I can be expressed in this form, okay, or this form. Remember, we talked about left or right ideal, okay? So any of this form for some R in the ring R. So if R is a commutative ring, it means it will satisfy this, right? And that principal ideal generated by A, which is A that is generating it, is denoted this way. So we always denote the principal ideal. This principal ideal is denoted this form, and this is how its elements look, okay? The principal ideal. So every element in I can be expressed in this form or this form. That's when we have a principal ideal, okay? So basically it's a collection of all the elements generated by A, okay? That's the principal ideal. Okay, so the next definition you need to recall basically is a field, because you need it in one of the lemmas I'll be proving shortly. So a field is a set with two operations, addition and multiplication, where both form abelian groups, okay, excluding the zero multiplication, right? And this multiplication distributes over addition. Now this field, it's a ring where every non-zero element has an inverse. So if I pick A in my field, say R, which is a field, it has an inverse such that A times A inverse will give me my identity, okay? So that's what it means. So it always has an inverse once it is a field. Okay, so let's move forward. So we start with examples. Now the first example says we should show that any set of this form, so if you have a set of this form, so it could be 4 as my multiples of 4, that it is an ideal. It should prove that's an ideal. So to show it's an ideal means that, remember what an ideal is. It's both left and a right? So we need to show it's an ideal. So it's a ring modulo, multiples of n, where n could be any number, right? Because it's not specific. But I could choose to give you a specific number and actually to show it's the same procedure, just that n will now be a number, right? Okay, so we have the set. We're told this set looks like this. This is how it is. So you need to know how to write it out. So well, it's multiples of n. So this collection of all. So x, and it's nx. So that means I will have x, 2x, 3x. Those are elements in the set. 4x. Keeps going till you get to the largest possible n x that you can think of. Okay, so those are how the elements are in this particular set. So we're to show that it's an ideal. What do we do then? So we first test the left, right, and then we test the right, and we have two identities it must satisfy, right? The identity that if you take A minus B, it will be in the ideal A, right? And if you multiply by the left A, it will be in A. So we check this to check for the left ideal. So as you can see on the screen, we have chosen two arbitrary elements in A comma B, but we know A is the set. So every element in this set, they look like this, right? Okay, so we just choose A and B. So we need to show that A minus B will give us results back in A, right? So now A comma B is from the set of integers modulo n, right? Multiples of n, not integers modulo n, but multiples of n. So if it's multiples of n, it means that my A could be, say, nx and B could be ny, where x and y are arbitrarily chosen elements in the set of integers. So what happens? So we have A minus B. We know what A is. It is nx. we know what B is. It is also NY. So wherever we see A, we put NX. Wherever we see B, we put NY. So the minus just follows for some X, Y, and Z, as you can see up there. So you know we're working with integers. So since we're working with integers, it satisfies the condition that I can factor out N, and I'll be left with X minus Y. Okay, where factorization in N multiples of the integers NZ. Okay, so is it not clear? X minus Y definitely is going to give me an integer. If you subtract X minus Y for any value you get, it will be an integer, right? So since it's going to be an integer, it means that truly this element, this thing, all of this lies in A, where A is our multiple of N, right? So we have satisfied the first condition that anytime we take A minus B, the value you get will be in NZ. So we finished the first condition to be satisfied. The next condition now is to show that if I multiply on the left hand side by R, and we pick A, where we know what A is my NX, that it will give us a value that will be in NZ, right? Because that's what we must get for NZ to be an ideal. Okay, so we check. So R times A, so there's R, we know A is NX, so plug it in, and factorization as it is the properties of elements in NZ, and clearly this would also be an element in A, which is also in NZ. And since both of the conditions are satisfied, the first one, which is the A minus B, we got that's definitely in NZ, right? And we got that R times A also was in NZ. So if that happens, clearly this is a left ideal. So this is a left ideal. So we've succeeded in showing that NZ is a left ideal. We need to show it's a right ideal. So that's what we do next. Same procedure, but now we don't need to check the first condition, right? Because by the proof earlier, we have shown that this was satisfied, right? So we need to only check for A times R, so R multiplying on the right side. So that's what we're doing here. And same procedure. You just go through and you find that this is also satisfied. So since both of them, we have that it's a right ideal here. So since both are right and left ideals, automatically we have an ideal. Okay, so you can pause the video to read through the screen because I've really flown here and explaining, I didn't read through all the sentences. So in class, I'll also still go over the video. Okay, so let's move forward. Next is lemma, which is the last thing we're going to be doing in the course of the proof in this video today. So the lemma says that if you have a ring, and it's a commutative ring, remember we had defined a commutative ring, we had defined a field earlier. Yeah, there it is. A field is a set with two operations, addition and multiplication, and such that in a ring, every non-zero element has a multiplicative inverse, right? So we have a field, right? And we had defined the principal ideal. Okay, so we'll be needing those definitions in the proof of this lemma. So we have a commutative ring with identity. Then it says that once you have that, then R is a field if and only if its ideals are the zero ideals and R itself. Okay, so meaning that R has no proper ideals. Okay, so we're to prove this. So you can see that there's an if and only if condition. In 203 we had defined when we have an if and only if condition. There's a two-way proof, right? So we'll prove this direction first. You can choose to prove whichever direction you want first, but I will be in this video proving in the direction you can see on the screen. So meaning that we're going to accept that it is a field first. So we accept that it's a field, and we're going to prove that the only ideals would be zero ideals and R itself, meaning that R has no proper ideal. So let R be a field. Now, if it's a field, remember the definition of a field, it means that it has inverses, right? Okay, so let's continue. So we can get a proper ideal, say I. Assume there is, so we're proving by contradiction. That's what it means, because we have said that there is no proper ideal. So let's assume there's a proper ideal. Say I and R, meaning that I is not equal to R, right? It's just contained in R. Now, since I is an ideal, an additive subgroup of R, you can pick any two elements A, B in R, such that A, B will be satisfying the condition in I, right? and meaning that I is not going to be empty, right? Because if you can get two elements and they'll be in I, it can be 0, right? Okay, but then we know that R is a field, right? So there's identity, it has additive inverse. Okay, so then because I is not empty, I can pick an X in it. X not equals to 0, R being a field, we know that we can pick an element R will not be 0, and it will have its inverse such that this condition is satisfied, right? So if this condition is satisfied and I get I, it is in I, it means that I is also, because it's an ideal, right? It satisfies this. You agree that this definitely will be in I, because I is an ideal and it satisfies the multiplication, as we can see up here, right? Okay. Now, R is the same as R times 1, and clearly this will lie in I too, because it's an ideal. Also because I is an ideal. So that's why that's the explanation I'd given. So now, if every time I pick R, I multiply by 1, I will get I. It means that for all R in my big R, right, R1 will lie in I. Clearly, R is the same as I, which is what we've gotten here. So if that is the case, this is a contradiction, because our initial assumption had said that I is a proper ideal. And if it's a proper ideal and now we're getting that it is equal to I, we have a contradiction. So if it's a contradiction, it means that the other part of our theorem, which is what we want, that the only ideals definitely are the 0 ideals and R itself. So we've proven the first direction. So therefore, the only ideals of R are the 0 and R itself. Okay, the next direction is where we're going next. So the next direction, we're going to be accepting that the ideals, the only ideals, are the 0 ideals and R itself. So we need to prove that R is a field. So let's go. Now let A, sorry, the A is looking like the normal A, but let A be a non-zero element in R. So we pick a non-zero element A. Consider the principal ID generated by A, so definitely to look like this. If it is the principal ID, remember we had done definition. We could choose to use this notation or just write it in this form. Now this ideal we already know consists of elements of this form, right? Where R are in this. Okay. Now the only ideals again are what? 0 and R. So it means that this principal ideal is either equal to the 0 ideal or R itself, right? Okay, so let's move forward. Now, if that is the case, okay, it will mean that these are the only condition, right? A cannot be 0. Why? Because it is the one generating the entire, it's generating all the elements in the ideal. It can't be 0 because A is a non-zero element. Remember, we had even chosen it, so where is it? Let A be a non-zero element, okay? And it's generating the entire ideals, right? So if this is non-zero, it means that this A will be equal to R. Okay, because A is equal to R. And remember we said that the lemma said that what kind of R do we have? It says it's a commutative ring with identity, right? Okay, so let's move forward now. It means that the multiplicative identity, must also be in A. Thus, there exists an R such that RA will be equal to 1. Remember that this is the generator and all its elements look like this, right? They are of this form. Okay, so it means that RA will be equal to 1. Okay, if RA equals to 1, it means there's an inverse somewhere, right? Because 1 is the identity. So this means that A has a multiplicative inverse, R in R. Since A, which is this A, remember, was an arbitrarily chosen non-zero element, every non-zero element in R has a multiplicative inverse, therefore R is a field. And that completes the proof. So there's a lot of English here, but I believe by the time you go over the video a second time, or even several times, you will be able to understand the steps in the proof. Okay, these are the references and